Good evening, all. Myself, Dr. Abhishek Tiwari. Today, we are going to discuss manufacturing processes, and in this, we are going to discuss metal casting, mold design involving feeding, gating, risering. So, this is the outline of the presentation. First, we are going to discuss what is manufacturing process, what are different types of manufacturing processes. Then, we will discuss metal casting, and then we will discuss mold design involving feeding, gating, and risering. So, what is manufacturing process? So, manufacturing is an economic term for making goods and services available to satisfy human wants. Manufacturing involves a series of related activities and operations like product design and development, material selection, what materials we need for the manufacturing process, and then process planning, what are the different types of processes involved, and then inventory control, what are the assets required, what are the different type of items required for the manufacturing process, and then quality assurance after the product has been made. Using manufacturing process, how is its quality, so that there is no complaints after it has been launched in the market, and then finally the marketing part. So the principal type of manufacturing is can be classified in three types: process type manufacturing, fabrication type manufacturing, and then assembly type manufacturing. So process type manufacturing involves continuous flow of materials through a series of process steps to obtain a finished product like chemicals, and fabrication type manufacturing involves manufacturing of individual parts or components by a series of operations such as rolling, machining, and welding. And an assembly type of manufacturing is done by putting together parts and components to get a complete product, such as a machine. So, types of manufacturing processes, and it can be based on constant mass processes, it can be based on metal removing processes, it can be based on material addition processes. So, if we consider constant mass processes, for example, casting, metal forming processes, and powder metallurgy processing and heat treatment. So, in casting, there are various types of castings like sand casting, cell mold casting, precision investment casting, plaster mold casting, permanent mold casting, die casting, centrifugal casting. And in metal forming processes, there can be different type of metal forming processes like rolling, drop forging, press forging, upset forging, extrusion, wire drawing, sheet metal operations. And then in metal removing processes, as the term clearly defines that we are going to remove metal in this process. So, like for example, if we machine any component, then we are going to lose some part of metal. So, for example, we do turning in lathe machines, so turning, drilling, milling, shaping, planing, sewing, broaching. In all these processes, we are going to lose some metal. Second is grinding and finishing. For example, in metallurgy, we do sample polishing. So in this also, like we grind it against emery paper. And third one is unconventional machining. And then we can have processes which are based on material addition processes. For example, if you want to repair any component, then we can do welding or any elite processing. For example, we can do gas welding, electric arc welding, electric resistance welding, thermite welding, cold welding, brazing, soldering. Then second type in this is mechanical joining. For example, we can do bolting and riveting. So you know nut and bolts, and so that kind of bolting and riveting can be done. Then we are going to discuss metal casting. So what is metal casting? So metal casting is a process in which molten metal flows by gravity or other force into a mold where it solidifies in the shape of mold cavity. Then we have in metal casting, first we melt the metal and then pour it into a mold and then let it cool so that it can solidify. Then casting includes both casting of ingots and casting of shapes. So ingot, it's a metallurgical term. For example, if we have some like rectangular bar kind of casting, then it's called ingot. And the term ingot is usually associated with primary metal industries. So it describes a large casting that is simple in shape and intended for subsequent reshaping by processes such as rolling or forging. So this is a typical metal casting process in which we are pouring the molten metal in this mold. So this is the metal casting process. So this is the typical metal casting after we have done the metal casting process. So now we are going to discuss what are the different parts involved in the metal casting. First one is pattern. So uh, we are going to discuss what are the types of patterns and allowances. So a pattern is a full-sized model of the part or the model of metal casting that we have to manufacturing. We have to manufacture, and it is enlarged to account for shrinkage and machining allowance in the final casting. Then material used to make patterns include wood, plastics, and metals. Wood is a common pattern, but it tend to warp. So it can be subjected to warping, and which is not good for a pattern to warp. So it can be abraded by sand being compacted around it, thus limiting the number of times we can use it. And metal patterns are more expensive, but they may last longer. And plastic represents a compromise between wood and metal, so it's in between the wood pattern and metal pattern. So now we can have a solid pattern or a split pattern. So as we can see in this picture, this is a solid pattern and this is a split pattern. So the simplest pattern we can think of is made of only one piece and is called solid pattern, which has same geometry as the casting, and it is adjusted in size for shrinkage and machining. Although it's easy to fabricate, it is not the easiest to use in making the sand mold. Determining the location of the parting line between the two halves of the mold for a solid pattern can be a problem. Incorporating the gating system and sprue into the mold is left to the judgment and skill of the foundry worker in case of solid pattern. And solid patterns are generally limited to very low production quantities. So generally we use this kind of split pattern. We have the two halves of the pattern. So a split pattern consists of two pieces dividing the part along a plane coinciding with parting line of the mold. Split patterns are appropriate for complex part geometries and moderate production quantities. Parting line of the mold is predetermined by two pattern halves rather than operator judgment. So next one is match plate pattern. So for higher production quantities, match plate pattern, or we can say cope and drag patterns are used. In match plate or cope and drag patterns, the two pieces of the split pattern are attached to the opposite side of the wood or metal plate. Holes in the plate allow the top and bottom cope and drag sections of the mold to be aligned accurately. So, so that these are aligned. So in this we have this match plate pattern. So in this we are matching with the plate. Cope and drag pattern are similar to match plate pattern, except that split pattern halves are attached to separate plates so that cope and drag sections of mold can be fabricated independently. So in this actually in match plate pattern we have only one plate, but in cope and drag pattern we have two plates. So it is like one type of match plate pattern, but we have two plates instead of one plate. The graphic include gating and riser system in cope and drag patterns. Then, while making pattern, certain dimensional allowances must be given in the pattern so that casting obtained is of required specifications. These include shrinkage allowance, draft or taper allowance, machining allowance, wrapping or shaking allowance, distortion allowance. Now we are going to discuss shrinkage allowance. So allowance added to pattern to compensate for metal shrinkage that takes place while the metal solidifies. All metals except bismuth and gallium solidifies, and the contraction of metals and alloys is always volumetric, but the contraction allowances are always expressed in linear dimensions. Next is draft or taper allowance. So the taper provided on vertical surfaces of a pattern to facilitate its easy removal from the mold without excessive wrapping or breakage of cavity edges. The amount of taper varies with type of pattern. The taper on inner surface should be greater than on the outer surface. The amount of taper varies from 0.5 degree to 1.5 degree and may be reduced to less than 0.5 degree for larger castings. Wooden patterns require more taper than metal patterns because of greater frictional resistance. Then we have machining allowance. So extra material provided on certain details of casting so that it may be machined to exact dimensions, and it depends on factors such as casting process, size of casting, degree of finish, machining method, and metallic alloy from which casting is made. The amount of this allowance varies from 1.6 mm to 12.5 mm. The ferrous metals require more machining allowance than non-ferrous metals. So, for example, for iron, stainless steel, or different type of steels, more machining allowance is required compared to, for example, for non-ferrous metals like aluminium, copper. Then we have raping or shaking allowance. So this is provided to compensate for enlargement of mold cavity because of excessive wrapping. In small and medium-sized castings, this allowance can be neglected, but in larger castings, this allowance is considered by making the part slightly smaller than the casting. The allowance is a negative one as the pattern is made smaller to allow shaking operation. Then we have distortion allowance. So it is provided on the pattern to compensate for possible distortion of the casting because of unequal cooling rates of different sections of the casting and uneven internal stresses. This allowance depends on the judgment and expertise of the maker who understands the shrinkage characteristics of the metal. So a typical metallurgist can decide what distortion allowance is required for making a pattern. Then we have sand casting, and on this we are going to discuss what are the sand properties. So, what are the sand properties required for doing sand casting? First is permeability. This property allows gases to escape easily from the mold. Higher the silt content of the sand, lower is permeability. If mold is rammed too hard, its permeability will decrease. Then second point is strength and cohesiveness. So this is defined as a property of holding together of sand grains. A molding sand should have ample strength so that mold does not collapse or get partially destroyed during conveying, turning over, or closing. Strength grows with density, clay content of mixture, and decreased size of sand grains. Then we have the third property is refractiveness. So it is the ability of molding sand mixture to withstand the heat of melt without showing any sign of softening or fusion. It increases with grain size of the sand and its content and with the diminished amount of impurities and silt. Fourth property is the plasticity or flowability. This property allows the sand to easily take any desired shapes. Fifth property is the collapsibility. It is the ability of the molding sand mixture to decrease in volume to some extent under compressive forces developed by shrinkage of metal during freezing and subsequent cooling. Collapsibility permits the molding sand to collapse easily during shakeout and the core of the permits the core to collapse easily during its knockout from the cooled casting. Lack of collapsibility may result in formation of cracks in the casting. It depends on the amount of quartz sand and binders and their type. Sixth property is coefficient of expansion. Sand should have low coefficient of expansion. Seventh property is chemical resistivity. Sand should not chemically react or combine with molten metal. Eighth property is adhesiveness. It is the property of the sand mixture to adhere to another body. Sand should cling to the sides of molding boxes so that it does not fall out when flasks are lifted and turned over. It depends on the type and amount of binder used in the sand mixture. Now, what are the constituents of sand? Sand, in its natural or moist state, is called green sand. It is a mixture of silica sand with 20 to 30% clay, having total amount of water from 6 to 10%. Composition of green sand is as follows. Here, silica has up to 75% content, and clay is about 8 to 15%, and bentonite is between 2 to 5%, and coal dust is between 5 to 10%, and water is between 7 to 8%. A large proportion of silica gives a refractory sand, but if in excess it destroys its cohesiveness. The presence of alumina gives the sand its clay content, which acts as a binder, but if it is in excess, then it destroys the permeability of the sand. Metallic oxides and lime, if it is in excess, then it impairs the refractory quality of the sand and increases its fusibility. Now, what are the steps involved in the metal casting? So, first is preparation of a pattern. Second one is preparation of molding sand. Third one is preparation of mold and cores. And fourth is melting the metal. Fifth one is pouring of metal into mold. Sixth is cooling and solidification. Seventh is removing the casting from mold. Fatling. Eighth is fatling. So fatling is a very important step. It is cutting off the unwanted projections in the form of gates, rises, etc. And ninth is heat treatment. And tenth is testing and inspection of any defects in the metal casting. So first is mold core making. Molding is an art of making sound mold out of sand by means of pattern and cores so that metal can be poured into molds to produce casting. To form the mold cavity, traditional method is to compact the molding sand around the pattern for both cope and drag in a container flask. The packing process is performed by various methods. The simplest is hand ramming, accomplished manually by a foundry worker. Various machines have been also developed to mechanize the packing procedure. So this is typical mold making. This is the plan of the mold box, and this is the section of mold box assembly. This is scope and track, two parts of the mold, and this is runner, riser, vent holes. So this is scope, this is drag, this is facing sand, this is box fitting sand. So this is the complete mold ready for pouring. An alternative to traditional flask for each sand mold is flaskless molding, which refers to use of one master flask in a mechanized system of mold production. Each sand mold is produced using the same master flask. Cores are made in simple wooden, metallic, or plastic core boxes. The simple method of core making is similar to that of mold making. The sand mixture is rammed into core box with a wooden rammer. Sometimes cores may need reinforcement with wire or nails in order to provide internal support so that they may not collapse while handling. The core sand mixture is rammed by hand or pneumatic rammers. For production work, machines are used for core making where core sand mixture is rammed by jolting, squeezing, or blowing. Molds are of following two types: temporary molds. These molds are destroyed at the time of removing castings from them, for example, sand molds. And permanent molds, these molds are used in die casting, and these molds are used time and again. And examples are metallic molds. Sand molds are often classified as green sand, dry sand, or skin dried molds. Green sand molds are made of a mixture of sand, clay, and water. The word green referring to mold containing moisture at the time of pouring. A dry sand mold is made using organic binders rather than clay, and the mold is baked in a large oven at temperature ranging from 200 degrees centigrade to 320 degrees centigrade. Oven baking strengthens the mold and hardens the cavity surface. A dry sand mold provides better dimensional control in the cast product compared to green sand mold. Compared to green sand molding. In a skin-dried mold, the advantage of a dry sand mold is partially achieved by drying the surface of a green sand mold to a depth of 10 to 25 mm at the mold cavity surface using torches, heating lamps, or other means. A special bonding material must be added to sand mixture to strengthen the cavity surface. Additionally, chemically bonded molds have been developed that are not based on either of these traditional binder ingredients. Some of the binder material used in these no-bake systems include furan resins consisting of furfural alcohol, urea, and formaldehyde, phenolics, and alkyds oils. So in this you can see that we have this drag half of mold made by hand, and drag is ready to be rolled over in preparation for making the cope. This is cope mold rammed up. Here you can see in this figure. Now, according to the state of the core, cores may be classified as green sand cores, dry sand cores, oil sand cores, loam cores, metal cores. According to core position in the mold, cores are classified as horizontal core, vertical core, balanced core, cover core, hanging core, wing core. So these you can see in the picture. This is the horizontal core because this is horizontal, and this is the vertical core. This is balanced core. This is cover core. This is hanging core, and this is wing core. Now we are going to discuss the gating system. So it is the passageway in the mold melt for carrying molten metal to mold cavity known as gating system. Any gating system should aim at providing a defect-free casting. So here you can see this is the sprue, this is pouring basin, this is scope, this is drag, this is ingate, this is riser, and this is sprue base or well, this is choke, this is runner, this is skim bob, and this is mold cavity, this is the parting line, and this is the molding board. So this is a typical metal casting system. Now basic elements of gating system are, as I discussed in the previous slide, is pouring basin, sprue base or well, runner, skim bob, gates. So these I have discussed in the previous slide also. The pouring basin, in this molten metal from ladle is poured into the pouring basin, from where it moves into the sprue and through the runner to other areas. And in the sprue provides an entrance to mold cavity for the molten metal. It is connected to the mold in cavity by a gate or series of gates. Sprue base or bell. It is for enlargement along a runner whose function is to trap heavier and lighter impurities such as dross or eroded sand. It prevents these impurities from going into mold cavity. Now, gates, also called the in-gates, are openings. In this figure, we can see here, this is the in-gate. So, and these are the openings through which the molten metal enters the mold cavity. Shape and cross sections should be such that it can readily be broken off after casting solidification and also allow the metal to enter quietly into mold cavity. Gates may be top parting, bottom type, or step type. So here we can see this is top gate, this is parting gate, and this is the bottom gate. This is step gate. So we have gate in steps. Now we discuss riser. So this is the top riser, this is the end riser, this is the parting line. So these are the reservoirs designed and located to feed molten metal to solidifying casting to compensate for solidification shrinkage. It is a hole cut or molded in the cope to permit the molten metal to rise above the highest point in the casting. So there can be various types of riser like top riser, dead or cold, side riser, live or hot, open riser, blind riser. In all casting processes, metal must be heated to molten state to be poured or otherwise forced into the mold. So this I discussed about the metal casting. Now in the next lecture we can discuss about melting of metal in the metal casting process and the various furnaces involved in the melting of the metal for melting of the metal for metal casting process. This is how we will pour into the uh, gating system or in this we can this is the pouring cup actually, so we can pour the metal. So we will discuss some questions based on gate examinations. During the metal casting of a slab, the thickness of solid formed after time t is proportional to t raised to power 1 by 3, t raised to power 1 by 2, t raised to power 1, t raised to power 2. So for casting of a slab, volume upon area, and that will be equal to thickness, is directly proportional to t raised to power 1 by 2, where V is the volume, A is the area, and T is the time taken for solidification. So the correct answer in this is B. Now question number 2. In a sound casting, the last liquid to solidify is in runner, riser, gate, vent. For a casting with no defects, the metal in the riser is provided with facility to solidify last, so as to provide excess liquid metal to accommodate shrinkage of the cast product after solidification. So the correct answer is riser. Correct answer is B. Question number 3. Riser is not required for castings of grey cast iron, white cast iron, aluminium 4% copper alloy, aluminium 12% Si alloy. So risers are added as reservoirs to feed liquid metal to solidifying castings as a means of compensating for solidification shrinkage. And in grey cast iron, actually grey cast iron expands during solidification and thus risers should not be used. So thank you for your attention.